Here is a question that sounds like it should have a simple answer, the kind of question where you'd expect someone to say, "Oh, right, obviously," once you explain it clearly enough. And yet, when you really dig into it, when you actually follow the math and sit with the implications and let the scales of what we're talking about wash over you properly, the answer is anything but simple. It's one of those beautiful questions where the answer is simultaneously totally obvious and completely mind-bending, and by the time we're done tonight, I hope you'll feel both things at once. You look up at the night sky on a genuinely dark night, away from the cities and the light pollution, somewhere in the countryside where the horizon is low and the air is clear, and you see stars, thousands of them, blazing overhead in patterns that people have been drawing pictures through since before written language existed. It's overwhelming and humbling and beautiful all at once. Now pull out a pair of binoculars and suddenly thousands become tens of thousands. Point a small telescope at the fuzzy smudge of the Milky Way cutting across the sky, and you're looking at millions. Modern telescopes can see hundreds of millions of individual stars, and astronomers tell us, with as much confidence as the data allows, that the Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. 400 billion stars. I want you to actually try to feel that number for a moment, not just read it and move on. If you started counting right now, one number per second, without sleeping, without stopping for food or water or anything at all, counting 1, 2, 3, 4, how long would it take to reach 400 billion? You'd need about 12,675 years. Julius Caesar hadn't been born yet when you'd need to have started. The first cities were barely being built in Mesopotamia. That is how many stars we're talking about. And yet astronomers, astrophysicists, cosmologists, the people who spend their professional lives studying galaxies, will tell you with completely straight faces and total conviction that our galaxy, this galaxy stuffed to what feels like the brim with hundreds of billions of stars, is almost entirely, overwhelmingly, almost existentially empty. Not a little empty, not half full, empty in a way that is genuinely hard to communicate because our brains didn't evolve to process numbers this large or distances this vast. Empty in the specific sense that if you shrank the entire Milky Way down to the size of the continental United States, from New York to Los Angeles, from the Canadian border to the Gulf of Mexico, all 400 billion of its stars, every single one of them, would take up less combined volume than a single grain of sand sitting somewhere in the middle of Kansas. The rest of that continent-sized galaxy, completely, utterly, profoundly empty. That is the paradox we're going to unpack tonight, and it's a paradox that, once you understand it, changes the way you think about the universe. Because it turns out that the emptiness of galaxies isn't a bug in the design of the cosmos. It's not a failure of stars to fill available space, the way a half-empty refrigerator represents food not yet bought. The emptiness is a feature. It is the direct, inevitable consequence of how physics works at cosmic scales. It is the signature of gravity operating on matter over billions of years. It is, in a strange and profound way, the reason we exist at all. But before we start the video, please subscribe to my channel. Thanks, guys. So tonight we're going to work through this from the beginning. We're going to start with the raw numbers, the actual mathematics of how much space there is in a galaxy versus how much space the stars take up, and those numbers alone will be enough to make your jaw drop. Then we're going to go deeper into the question of why the emptiness has the particular shape it does. Why stars cluster in spiral arms rather than spreading evenly? Why there are vast regions of the galaxy where almost nothing is forming, and other regions that are blazing nurseries of new star birth? What role the invisible dark matter plays in sculpting the whole structure, and what the spaces between stars actually contain even though we call them empty. We'll talk about what happens when galaxies collide, and why collide is almost entirely the wrong word for it. And we'll zoom out to the even grander scale of the cosmic web, where the emptiness of individual galaxies turns out to be just a small-scale echo of an emptiness that extends across hundreds of millions of light-years in every direction. And finally, we'll connect all of this to the most haunting question the emptiness raises. If there are so many stars out there, all this real estate in the galaxy, why is there no evidence of anyone else home? That's the agenda. It's a lot. Let's start at the beginning of the numbers. Our galaxy, the Milky Way, is classified as a barred spiral galaxy. It has a central bulge, a denser, roughly spherical concentration of older stars near the center, and cutting through that bulge is an elongated rectangular bar of stars and from the ends of that bar spring 4 major spiral arms that sweep outward in graceful curves. The whole structure is a disk, flat as a dinner plate on cosmic scales, about 100,000 light-years across and roughly 1,000 light-years thick in our neighbourhood. Though it thickens considerably toward the centre, our solar system sits about 26,000 light-years from the galactic centre, tucked into a minor arm segment called the Orion Spur, which branches off the larger Sagittarius Carina arm. We are, in the grand galactic geography, a mid-suburb. Not the bustling centre, not the sparse outer edge, the comfortable middle distances. The Milky Way is estimated to contain somewhere between 200 billion and 400 billion stars. That enormous range, a factor of 2 essentially, reflects a genuine difficulty in counting. We can't step outside the galaxy to look at it from above. We're embedded in the galactic disk, surrounded by dust clouds that block our view of a significant fraction of the galactic plane, and many of the faintest stars, the dim, reddish, long-lived red dwarf stars that actually make up the majority of stellar objects, are too faint to detect individually at galactic distances even with our most powerful instruments. The European Space Agency's Gaia mission has been systematically mapping the positions and properties of stars in the Milky Way since 2013. As of its most recent data releases, Gaia has catalogued nearly 2 billion individual stars, but that's still less than 1% of the estimated total stellar population. Gaia's scientists estimate that by the end of the mission, better constraints on the faint-end stellar population will help, but significant uncertainties will likely remain in the total count. The honest answer is we don't know exactly how many stars our galaxy has, and we probably won't for a long time. But whether it's 200 billion or 400 billion, the fundamental character of the situation doesn't change. We're talking about a number of stars so large that if you counted 1 per second for your entire life, from birth to death, never sleeping, never pausing, you'd count somewhere around 2.5 billion, not even 1% of the way through. The number of stars in the Milky Way exceeds the total number of seconds that have elapsed since the Earth formed 4.5 billion years ago. It exceeds the total number of heartbeats in every human who has ever lived, by a large margin. And yet, this enormous number of stars is contained in a galaxy that is almost entirely empty. That's the extraordinary thing. That's the thing that takes work to actually believe. Section 2. Numbers that break your brain. The true scale of a galaxy. Let's get mathematical about this, because the math is where the real shock lives. A light year is the distance that light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers, or roughly 5.88 trillion miles. 1 light year. Our nearest stellar neighbour, Proxima Centauri, is 4.24 light-years away. That means the light you'd see from Proxima Centauri left that star more than 4 years ago. By the time it reaches your eye, 4 years have passed on Earth. 4 light-years. That's roughly 40 trillion kilometers. The fastest spacecraft humanity has ever built, the Voyager 1 probe launched in 1977, is currently travelling at about 17 kilometers per second, which is extraordinarily fast by any terrestrial standard. A bullet travels at maybe 1 kilometer per second. A commercial airliner travels at about 0.25 kilometers per second. Voyager is moving at 17 times the speed of a bullet, and at that speed, it would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. Agriculture was invented about 12,000 years ago. Modern Homo sapiens have only existed for maybe 300,000 years. We sent a spacecraft out in 1977, and it would need 73,000 more years to reach the nearest other star, which is our closest neighbour. Now hold that number in your mind, 4.24 light-years to the nearest star, and remember, the Milky Way is 100,000 light-years across. If Proxima Centauri represents the next house on the street, the diameter of the galaxy represents the distance from your house to the next city, an hour's drive away. And there are 300 billion other houses in that area. To understand how empty this is, let's work through the volume comparison properly. The Milky Way's disk can be approximated as a cylinder about 100,000 light-years in diameter and 1,000 light-years thick. The volume of this cylinder is pi times the radius squared times the height. Pi times 50,000, squared times 1,000 light-years cubed. which comes out to approximately 7.85 billion cubic light years. That's the galactic disk we're working with. Now let's think about the stars. The Sun has a diameter of about 1.4 million kilometers. In light seconds, the distance light travels in 1 second, which is 300,000 kilometers. The Sun is about 4.65 light seconds across. In light years, that's a tiny fraction, about 0.00000000531 light years per Sun diameter. That decimal point is followed by 6 zeros before the first significant digit. The Sun, the source of all the energy that sustains life on Earth, is, in light-year terms, almost incomprehensibly tiny. Now, to calculate the total volume of all the stars in the galaxy, let's make a generous simplification. Assume all 300 billion stars are exactly the size of the Sun. In reality, most stars are smaller. The majority of stars in the Milky Way are red dwarfs with diameters roughly half the Sun's or less. But let's be generous and use the Sun as our template. The volume of a sphere is 4/3 times pi times the radius cubed. The Sun's radius in light years is about 0.00000000266 light years. Cubed, that's roughly 1.88 times 10 to the power of negative 23 cubic light years. Multiply by 4/3 times pi and you get the Sun's volume, approximately 7.9 times 10 to the negative 23 cubic light years. 300 billion stars, each with that volume. 300 times 10 to the 9th times 7.9 times 10 to the negative 23 cubic light years equals roughly 2.4 times 10 to the negative 11th cubic light years. About 24 billionths of a cubic light year is taken up by all the stars in the Milky Way. And the volume of the galactic disk? About 7.85 billion, or 7.85 times 10 to the power of 9 cubic light years. The fraction occupied by stars, 2.4 times 10 to the negative 11, divided by 7.85 times 10 to the 9. That equals roughly 3 times 10 to the negative 21. 3 times 10 to the negative 21. That is a decimal point followed by 20 zeros followed by the number 3. Stars occupy about 0.0000000000000000000000003 of the galactic disk's volume. 3/100 quintillionths, if you want to try to say it out loud. As a percentage, approximately 0.00000000000000000000003%. This is the number at the heart of the paradox. All those billions of stars, and they fill essentially nothing. Not a fraction of a percent, not a billionth of a percent. A number so small it doesn't have a name we commonly use in everyday life. Now let's try to make this feel real with some analogies, because numbers that extreme don't naturally register as real things. Imagine you have a swimming pool, a standard Olympic swimming pool, 50 meters long, 25 meters wide, and 2 meters deep, holding 2.5 million liters of water. Now imagine that pool represents the volume of the Milky Way's disk. How much water would represent all the stars? Working out the scale, you'd end up with approximately a single drop of water, not a spoonful, not a teaspoon. One drop, about 0.05 milliliters, represents the total volume of all the stars in the galaxy when scaled to an Olympic pool. The rest of the pool, all 2.5 million liters minus that one drop, is empty galactic space. Or try this analogy, which I think is the most viscerally effective. The National Radio Astronomy Observatory notes that the average distance between stars in the Milky Way is roughly 5 light years. One widely cited analogy goes like this. If the Sun were shrunk to the size of a period at the end of a sentence, a dot about 0.5 millimeter in diameter, then at that same scale the nearest star, Proxima Centauri, would be another period-sized dot sitting about 1.5 kilometers away. 1.5 kilometers of completely empty space between two tiny dots, each representing an entire star. Multiply that out across 300 billion stars spread across a disk 100,000 light-years wide, and you get a sense of what the Milky Way really looks like. A handful of barely visible specks scattered across an expanse that dwarfs anything in human experience. One more way to think about this. Imagine you could transport yourself instantly to a random location within the Milky Way's disk. You look around. What would you see? Almost certainly nothing in your immediate vicinity. No star within light years. Just darkness in every direction, with perhaps a few distant stars visible as points of light, separated from you by unimaginable distances. The odds of ending up near enough to any star that you could identify it as a disk, rather than a point, would be essentially zero. The galaxy looks full from outside, with its beautiful arms and dense central bulge. From inside, from most locations within it, it looks like absolutely nothing. This is the fundamental fact about galaxies. They are mostly empty by an almost incomprehensible margin. The scale of the emptiness absolutely defeats the impressiveness of the number of stars. The stars are abundant only in the way that a few grains of sand scattered across a continent are abundant. Yes, they're there. Yes, there are many of them. But they constitute nothing in terms of filling the space they inhabit. Now the question becomes, why are they distributed the way they are? Why not spread uniformly across the disk? Why cluster in arms and bulges? And why, in the vast spaces between the stars, is there something rather than total nothing? To answer those questions, we need to go back to the very beginning of cosmic history. Section 3. The Anatomy of Interstellar Space. The Ocean Between Stars. People call space empty, and in the sense we've been discussing, empty of stars, empty of anything you could see without instruments, that's fair. But the space between stars is not empty in the physicist's sense of the word. It is filled with one of the most complex, dynamic, and scientifically fascinating environments in the universe, the interstellar medium. The interstellar medium, usually called the ISM, is the material that occupies the space between stellar systems within a galaxy. It consists of gas and dust, threaded through with magnetic fields and permeated by cosmic rays and radiation, and it exists simultaneously in multiple different physical states with wildly different properties. Understanding the ISM is crucial for understanding galactic emptiness, because the ISM is the raw material from which stars form, the medium through which stellar energy propagates, and the thermodynamic environment that determines where and when star formation can occur. On average, the ISM contains about 1 hydrogen atom per cubic centimetre. That is the number that gets cited most often, and it's worth dwelling on what it means. Your bedroom right now contains roughly 3 times 10 to the power of 25 molecules of air per cubic metre. That's a 3 followed by 25 zeros. The average interstellar medium contains 1 million atoms per cubic metre, or about 10 to the power of 6. Your bedroom air is roughly 30 million trillion times denser than the average interstellar medium. If you could somehow extract all the air from your bedroom and replace it with typical interstellar medium, and then suddenly be standing in it, you would be in what would classify for all practical purposes as a perfect vacuum. Far better than the best vacuum chamber we have ever constructed on Earth. And yet that 1 atom per cubic centimetre number is the average across a medium that is strikingly non-uniform. The ISM is not like a glass of water, relatively the same throughout. It is more like a churning, turbulent ocean, with layers and currents and regions of very different character, existing in multiple phases simultaneously. Astronomers classify the ISM into several distinct phases, each with its own range of temperatures and densities. The hottest phase is called the hot ionized medium, or coronal gas. This is plasma superheated by supernova explosions and the powerful stellar winds of massive stars to temperatures ranging from about 100,000 to 10 million Kelvin. At those temperatures, all the electrons have been stripped from the atoms. There are no neutral atoms left, just bare atomic nuclei and free electrons flying around at enormous velocities. The density of this hot phase is extraordinarily low, fewer than 1/10,000th of a particle per cubic centimetre, sometimes much less. The hot ionized medium fills a large fraction of the total volume of the galactic disk. Some estimates suggest 20 to 50% of the volume, though the exact fraction is debated. In terms of mass, it's far less significant because it's so thin. At somewhat lower temperatures, around 10,000 Kelvin, you find the warm ionized medium. This phase is still ionized, meaning the hydrogen atoms have lost their electrons, but it's cooler than the coronal gas. Its density is typically around 0.01 to 0.1 atoms per cubic centimetre. The warm ionized medium is responsible for the beautiful emission nebulae you see in astronomical photographs: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula. These are regions where massive young stars are pouring out ultraviolet radiation so intense that it ionizes all the gas within hundreds of light years, causing it to glow. In the colour images from telescopes like the Hubble Space Telescope, The warm ionized medium appears in various colors depending on the specific emission wavelengths. The red of ionized hydrogen, the blue-green of doubly ionized oxygen, the red-orange of ionized sulfur. Then there's the warm neutral medium, at temperatures of a few thousand Kelvin and densities of about 0.1 to 1 atom per cubic centimeter. This phase represents hydrogen that hasn't been ionized. The electron and proton are still bound together, but is warm enough that the atoms are moving around with significant thermal energy. At lower temperatures still, below about 100 Kelvin, you find cold neutral hydrogen, clouds of atomic hydrogen at densities of 1 to 100 atoms per cubic centimeter. These clouds were some of the first structures mapped in the ISM, using radio telescopes in the mid-20th century. Hydrogen in the neutral atomic form emits a characteristic radio wave at a wavelength of 21 centimeters, a signal produced when the electron in a hydrogen atom undergoes what's called a spin-flip transition, switching from having its spin parallel to the proton spin to having it anti-parallel, releasing a photon of that specific wavelength. Radio telescopes can detect this 21 centimeter emission through the dust that obscures optical light, giving astronomers a way to map the distribution of neutral hydrogen throughout the entire galactic disk in a way that optical telescopes cannot. And then, at the coldest end of the spectrum with temperatures as low as 10 to 30 Kelvin, barely above absolute zero, you find the molecular clouds. These are the densest and most important structures in the ISM for our purposes, because they are where stars are born. In a molecular cloud, the temperature is low enough and the density is high enough that hydrogen exists not as individual atoms but as hydrogen molecules, two hydrogen atoms bound together. The densities in molecular clouds range from about 100 to tens of millions of molecules per cubic centimeter. Giant molecular clouds, the GMCs, span tens to hundreds of light years and contain masses equivalent to 100,000 to 10 million times the mass of the Sun. The Milky Way contains approximately 1,000 of these giant molecular clouds, and they account for roughly half of all the mass in the ISM despite being the smallest and rarest of the ISM phases by volume. They are the seeds from which stars grow. Beyond the gas, about 1% of the ISM's mass consists of solid particles, interstellar dust grains. These grains range in size from a few nanometers, smaller than many virus particles, up to about a micrometer, and they're made of silicate minerals, graphitic carbon, polycyclic aromatic hydrocarbons, and water ice, depending on where in the ISM they formed and what conditions they've experienced. The dust is responsible for the dark lanes you see crossing the faces of edge-on galaxies in photographs, and for the distinctive reddening of starlight. Distant stars appear redder than they actually are because dust grains scatter blue light more efficiently than red, so the blue light gets bounced away while the red light gets through. Astronomers have to correct for this effect when measuring the properties of distant stars. The dust also plays a profound role in the chemistry of the ISM. The surfaces of dust grains act as catalysts and reaction sites for the formation of complex molecules. In the cold, dense interior of a molecular cloud, atoms and simple molecules stick to dust grain surfaces and react with each other in ways they couldn't in the gas phase. This is how molecular hydrogen forms. Two hydrogen atoms stick to a dust grain and bond together, then get liberated back into the gas. And this is how more complex molecules form as well. Astronomers have now detected over 200 distinct molecular species in the interstellar medium, identified by the characteristic wavelengths of light they emit or absorb. These include water, ammonia, carbon monoxide, formaldehyde, methanol, ethanol, glycolaldehyde, a simple sugar precursor, and even amino acid precursors like glycine. The interstellar medium is, in this sense, an enormous chemistry laboratory, running experiments in extreme low temperature, low pressure conditions across volumes measured in light years, over timescales measured in millions of years. The organic molecules that eventually end up on newly forming planets, the prebiotic chemistry that may kickstart the path to life, have often been pre-assembled in the interstellar medium before those planets even form. The interstellar medium is also threaded through with magnetic fields. The Milky Way has a large-scale magnetic field, weaker than almost any human technology could produce, typically a few microgauss in strength, compared to the 0.5 Gauss of Earth's magnetic field, or the Gauss range fields of a refrigerator magnet, but extending across the full size of the galactic disk and playing crucial roles in ISM dynamics. The magnetic field provides support against gravitational collapse in molecular clouds, regulating the rate of star formation. It channels the flow of cosmic rays, high-energy charge particles, through the galaxy. It couples to the ionized gas through magnetic pressure, helping to support that gas against gravitational compression. So when we say the space between stars is empty, we need to be specific. It is empty of stars. It is not empty of gas, dust, magnetic fields, cosmic rays, photons, neutrinos, dark matter, or the quantum energy of spacetime itself. It is an extraordinarily thin, rarefied, complex medium that is nevertheless there, threaded through every cubic light-year of the galaxy, forming the ocean in which the stars float and from which new stars will eventually form. This ocean of interstellar material is what makes galaxies dynamic. Stars form from it, enrich it with heavy elements when they die, heat it, and compress it with their radiation and supernova explosions, and eventually return most of their mass to it. The ISM is a cycle, a continuous recycling of matter from diffuse clouds to dense stars and back to diffuse clouds again, repeated over and over through the history of the galaxy. Our Sun, right now, is swimming in the interstellar medium. The local bubble, a region of unusually hot and thin ISM created by supernova explosions some millions of years ago. We are surrounded by the aftermath of ancient stellar deaths, drifting through a sea of ghost plasma, and we don't even notice. Section 4. Why stars form in clusters, not everywhere. If the interstellar medium fills the galaxy, and if the ISM contains the raw material from which stars form, then why don't stars form everywhere? Why are there vast expanses of the galaxy where the ISM sits quiescent, cold, undisturbed, never collapsing into new stars, while other regions are crackling nurseries of starbirth? The answer to this question is at the heart of why galaxies have the particular texture of emptiness they do, why some regions are denser with stars and others are more sparse, and it comes down to a beautiful interplay of forces that has been operating since the first stars ignited in the early universe. To form a star, you need gas to collapse under gravity. That sounds simple. Gravity pulls things together. Gas pulls itself together. Collapse happens, star forms, done. But this naive picture misses the most important part of the physics. Gas pushes back. When gas is compressed, it heats up. When gas heats up, its pressure increases. An increased pressure means the gas pushes outward with more force, resisting further compression. This is the fundamental thermodynamic tension at the heart of star formation. Gravity pulling in versus thermal pressure pushing out. Star formation only happens when gravity wins this tug-of-war, when the gas is dense enough and cold enough that gravity can overcome the outward thermal pressure and drive the gas to continue collapsing all the way to stellar densities. In the early 19th century, the British physicist James Jeans worked out the mathematics of when this tug-of-war tips in gravity's favour. His result is now called the Jeans criterion. A gas cloud will collapse to form a star, or stars, only if its mass exceeds a critical value called the Jeans mass, a value that depends on the temperature and density of the gas. Specifically, the Jeans mass goes up with temperature and down with density. Hotter gas is harder to collapse, requiring a more massive cloud before gravity can win. Colder, denser gas can collapse with much less mass. Working through the numbers for typical ISM conditions illustrates why star formation is so localized. In the warm ionized medium, at 10,000 Kelvin and 0.1 atoms per cubic centimeter, the Jeans mass works out to be enormous, far more mass than exists in any realistic cloud. The warm gas simply cannot collapse to form stars. The thermal pressure is overwhelming. The same is true for the diffuse neutral hydrogen at a few thousand Kelvin. Even the cold neutral hydrogen clouds, at around 80 Kelvin and a few atoms per cubic centimeter, have Jeans masses of thousands to tens of thousands of solar masses, very large, but now at least in the range of what exists in molecular clouds. In the molecular clouds, the situation finally becomes favourable. At 10 to 30 Kelvin and densities of hundreds to millions of molecules per cubic centimeter, the Jeans mass drops to just a few solar masses. Individual collapsing cores within a molecular cloud can be only a few times the mass of the Sun, small enough that the available gas can actually form them. This is why star formation happens almost exclusively in molecular clouds, and why the distribution of star-forming regions in a galaxy follows the distribution of molecular gas. But wait, if the Jeans criterion is met inside a molecular cloud, Why doesn't the whole cloud collapse at once? Why does it fragment into individual stars rather than one enormous catastrophic collapse? The answer is turbulence. Molecular clouds are not quiescent. They are internally supersonic. The gas within them is moving at speeds faster than the speed of sound in that gas, in complex turbulent patterns. This turbulence creates a hierarchy of density fluctuations throughout the cloud, with some regions denser than average and others less dense. The denser regions have lower Jeans masses and can collapse more easily. They begin to fall inward while the less dense regions around them remain supported. As these dense clumps collapse, they fragment further. Within a collapsing clump, some regions again become denser than others and begin their own independent collapse, creating a branching hierarchy of structure all the way down from the cloud scale to the scale of individual star-forming cores. The result is that a single giant molecular cloud doesn't form a single star. It forms hundreds or thousands of stars, simultaneously collapsing from density fluctuations distributed throughout the cloud. This is why stars almost always form in clusters. The physics of turbulent fragmentation naturally produces clusters rather than isolated individuals. The most famous example is the Orion Nebula Cluster, a group of about 1,000 young stars between 1 and 2 million years old, all formed within the Orion molecular cloud, all still embedded in the gas and dust of their birth environment. The Pleiades, the famous Seven Sisters star cluster visible to the naked eye, are another example, a cluster of a few hundred stars that formed together about 100 million years ago, now slowly dispersing as their mutual gravitational binding weakens. Here is a crucial point for understanding galactic emptiness. Star formation is spectacularly inefficient. Of all the gas in a molecular cloud that could theoretically collapse into stars, only about 1 to 10% actually does. The rest gets blown away. The reason for this low efficiency is something astronomers call stellar feedback. When massive stars form, and a molecular cloud will typically produce some massive stars alongside the vast majority of lower mass ones, they are extraordinarily energetic. A star 10 times more massive than the Sun is roughly 10,000 times more luminous. Its ultraviolet radiation output is enough to ionize all the neutral gas within hundreds of light years of it, creating a bubble of hot plasma around it. The stellar wind of such a star, the constant outflow of charged particles from its surface, exerts radiation pressure on the surrounding gas, and massive stars typically live only a few million years before exploding as supernovae, events that release as much energy in a few seconds as the Sun emits over 10 billion years, creating blast waves that sweep outward through the ISM at thousands of kilometers per second. Collectively, the radiation, stellar winds, and eventual supernovae of the massive stars in a young cluster act like an explosion inside the molecular cloud, blowing away the remaining gas before it can collapse and form more stars. The cloud is dispersed. Star formation in that region ceases. The newly formed cluster of stars, now unshielded by their birth cloud, begins to drift apart under its own dynamical evolution, the stars gradually separating as random gravitational kicks send them off in slightly different directions over millions of years. This feedback-regulated, low-efficiency star formation has been operating in the Milky Way for about 10 billion years. Each cycle, cloud collapses, forms some stars, feedback blows away the rest of the cloud, cluster disperses, takes roughly 100 million years. The galaxy has undergone this cycle perhaps 100 times since it formed, and each cycle adds a modest number of new stars to the galactic population while leaving the bulk of the gas uncollapsed, drifting through the ISM until it cools and condenses again. The consequence for galactic emptiness is that even over 10 billion years of star formation, the galaxy has only converted a fraction of its available gas into stars. The Milky Way today still contains roughly 5 to 10 billion solar masses of cold molecular gas, the raw material for future star formation. The stellar mass of the galaxy is perhaps 50 to 60 billion solar masses, so the galaxy is not even close to running out of gas for new stars. It still has enormous reserves available, but the physics of feedback ensures that this gas converts to stars slowly, inefficiently, and in concentrated bursts in molecular clouds rather than uniformly throughout the disk. There is one more major factor that determines where star formation happens in a galaxy, and it operates at the scale of the whole galaxy rather than the individual molecular cloud. It's the spiral arm density wave, and it's the reason that the pattern of young star clusters and bright nebulae in a galaxy so beautifully traces the spiral arm structure. As the galactic disk rotates differentially, with the inner disk orbiting faster than the outer disk, the gas in the disk is constantly in motion. The spiral arms in a galaxy like the Milky Way are not fixed, rigid structures but density waves, regions of slightly elevated gravitational density that rotate through the disk at their own pattern speed, which is typically different from the rotation speed of the individual stars and gas clouds. As a gas cloud in the disk sweeps into a spiral arm region, it experiences a slight gravitational compression from the higher density environment of the arm. This compression can be enough to push the gas cloud over the threshold needed to trigger collapse. Star formation is enhanced in the arm region. The young, massive stars that form in the arm blow away their surrounding gas quickly and then age and cool over the next hundreds of millions of years. The older, cooler, less luminous population drifts away from the arm region and fills the interarm spaces. Meanwhile, the arm region itself is constantly being refreshed by new gas sweeping in and new star formation occurring. This is why spiral arms look blue and bright in photographs. They're lit up by the youngest, hottest, most massive and most luminous stars, which preferentially form in the arms. The interarm regions are populated predominantly by older, dimmer stars and have less active star formation and less raw gas. So the spatial distribution of stellar emptiness within a galaxy is, at its core, a map of star formation history, filtered through the dynamics of galactic rotation and shaped by the interplay of gravity, thermal physics, magnetic fields, turbulence, and stellar feedback. The arms are denser with young stars and active nebulae because the density wave compresses gas there and triggers star formation. The interarm regions are less active because the gas density there is lower and no strong trigger is driving collapse. And the overall level of star formation is kept low by feedback, ensuring that the gas reservoir is consumed slowly rather than all at once. Section 5. Dark Matter's Invisible Architecture. We've been talking about ordinary matter, the gas, dust and stars made of protons, neutrons and electrons, the stuff of everyday experience. But ordinary matter is not the dominant form of matter in the universe. It accounts for only about 15% of all matter. The other 85% is something else entirely, dark matter. And understanding dark matter is essential for understanding why galaxies have the shapes they do, why the stars are distributed in a disk of a particular size, why there are spiral arms, why the whole structure rotates the way it does. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with light in any way that we can directly detect. It doesn't emit radio waves or X-rays or infrared radiation. It doesn't interact via the electromagnetic force at all, as far as we know. This is why it was so hard to discover, and why it took decades of careful observation to convince the astronomical community that it was real. The evidence that convinced everyone came from rotation curves. When you measure the rotation speed of different parts of a spiral galaxy, how far stars and gas are orbiting around the galactic center at different distances from the center, you get a curve. Based on Newton's laws and the observed distribution of visible matter, you'd expect this curve to peak somewhere in the inner disk and then fall off as you move outward, because most of the visible mass is concentrated in the central region. This is exactly what happens in our solar system. Mercury orbits the Sun much faster than Pluto does, because most of the solar system's mass is concentrated in the Sun at the center, and gravitational force, and therefore orbital speed, falls off with distance. But when Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies in the 1970s, they found something completely different. The outer stars in galaxies were not slowing down the way they should. The rotation curves were flat. Stars at the outer edge of a galaxy orbited at roughly the same speed as stars much closer to the center. Some galaxies even showed rotation speeds that increased slightly with radius, the exact opposite of what visible mass distribution would predict. The only explanation that works is that there is a large amount of mass distributed throughout and around the galaxy that we cannot see, mass that extends far beyond the visible stellar disk and provides the extra gravitational pull needed to keep the outer stars moving so fast. That mass is dark matter. The dark matter is not distributed in a disk like the visible stars and gas. Because dark matter doesn't interact via the electromagnetic force, it cannot cool by radiating energy. And cooling is what allows ordinary matter to collapse into a flat disk. When gas falls into a gravitational potential and gets compressed, it heats up, then radiates that heat away as electromagnetic radiation, light, infrared, radio waves, etc., loses energy, and can therefore collapse further. This is the process that creates the flat, rotating disk of a spiral galaxy. Dark matter doesn't do this. Without electromagnetic cooling, dark matter particles lose angular momentum much more slowly, and instead of collapsing into a disk, they remain in extended, roughly spherical distributions, the dark matter halo. The dark matter halo of the Milky Way extends to distances of perhaps 600,000 light-years from the galactic center, 6 times the diameter of the visible galaxy. It contains roughly 1 to 2 trillion solar masses of dark matter, several times more than all the visible stars and gas combined. And it was there first. Dark matter clumped gravitationally before ordinary matter could, because dark matter didn't have to fight against the pressure of hot plasma in the early universe. By the time ordinary matter could begin to cool and condense, the dark matter halos were already in place, their gravitational wells ready to collect the infalling gas. Every galaxy forms within a dark matter halo. The halo is the gravitational container that determines how large the galaxy gets, how fast it rotates, and to some degree what shape it takes. The visible galaxy, the stars and gas that we can see, is a luminous fringe of the dark matter structure, concentrated in the densest region of the halo by cooling and condensation, while the dark matter itself remains in its extended spherical distribution. Understanding dark matter helps explain not just the gross structure of galaxies, but some of the fine details of why matter distributes itself the way it does. Computer simulations of galaxy formation that include dark matter, starting from the tiny density fluctuations of the early universe and following gravitational evolution forward through 13.8 billion years of cosmic time, produce structures remarkably similar to the galaxies we observe. Simulations that leave out dark matter produce structures that look very different from real galaxies. Dark matter is not optional for explaining the universe we live in, it is foundational. The distribution of dark matter also helps explain why spiral arms are such a common feature of disk galaxies. The galactic disk, embedded in a large dark matter halo, is susceptible to gravitational instabilities that naturally produce the density wave patterns we recognize as spiral arms. Computer simulations show that a rotating disk of gas and stars in a dark matter halo will naturally develop spiral arm structure over timescales of billions of years without needing any external trigger. The dark matter halo stabilizes the overall disk while allowing the internal dynamics of the disk, the differential rotation, the gravitational interactions between stars and gas, to develop the spiral pattern. There's also a recently published fascinating discovery. Dark matter may itself have spiral structure. A study published in Astronomy and Astrophysics in 2025 found evidence for spiral arm structures in the dark matter halos of Milky Way-like galaxies in computer simulations. These dark matter spiral arms arise from the gravitational interaction between the stellar spiral arms and the dark matter particles orbiting in the halo, a resonant coupling between visible and invisible matter. The dark matter responds to the gravitational potential of the stellar arms, with DM particles being deflected into arm-shaped overdensities that trace the stellar structure. This is a beautiful illustration of how intertwined ordinary matter and dark matter really are, even though they can't directly touch or see each other. Section 6. Spiral arms, galactic bars, and why structure emerges. We've touched on spiral arms already, but they deserve their own careful examination because they represent one of the most visually dramatic expressions of why galaxies have the particular texture of emptiness they do. Concentrations in some places, voids in others, all determined by physics. The spiral arms of a galaxy look at first glance like fixed structures. You look at a photograph of the Pinwheel Galaxy or the Whirlpool Galaxy, and you see arms that curl gracefully outward from the center, and it's natural to think, those arms are made of specific stars, arranged in that pattern, and they stay that way. But this is precisely wrong, and understanding why it's wrong is key to understanding how galaxies self-organize their matter. A galaxy doesn't rotate like a rigid body, the way a spinning top rotates, where every part completes one revolution in the same time. Instead, a galaxy shows differential rotation. Inner parts orbit faster than outer parts. Our solar system, 26,000 light-years from the galactic center, completes one orbit in about 225 to 250 million years. Stars closer to the center orbit much more quickly. Stars at the outer edge of the disk take much longer. If a spiral arm were a fixed group of stars, this differential rotation would destroy it quickly. The inner stars would rotate faster, pulling ahead of the outer stars, winding the arm tighter and tighter, until within a few rotation periods, perhaps 1 billion years or so, the arm would be wound into a tight, featureless ring. But galaxies billions of years old still show open, graceful spiral arms. They don't wind up. Something keeps them looking the same. The most widely accepted solution is density wave theory, formulated in the 1960s by the Chinese-American astronomers Chia Chiao-Lin and Frank Xu. On this picture, the spiral arms are not fixed groups of stars at all. They are standing waves in the density of the galactic disk, regions where the gravitational density is slightly elevated, rotating around the galaxy at a pattern speed that is generally different from the orbital speed of the individual stars. Stars and gas pass through the arm region, spend some time there in the elevated density environment, and then move on. The arm pattern persists even as its constituent material changes. The best analogy is a traffic jam on a circular highway. Imagine cars driving around a loop. Somewhere on the loop there's a slight narrowing or an on-ramp that creates a density build-up. Cars slow down, bunch up, pass through the congestion, and then speed up again. The congested region, the traffic jam, exists as a persistent feature of the highway, even though it's continuously made of different cars. Individual cars enter from the upstream side, traverse the jam slowly, and then exit downstream. The jam has a fixed position, more or less, but is made of constantly changing material. Galactic spiral arms work similarly. Gas and stars approach the arm from the upstream side. In the arm, the slightly elevated density produces a slightly stronger gravitational pull, causing gas to be compressed. This compression triggers star formation. The gas density in the arm exceeds the Jeans mass threshold, and molecular clouds collapse into new stars. The massive new stars that form blaze blue and bright, and some of them ionize the gas around them, creating the glowing nebulae that trace the arm in photographs. Then those newly formed stars pass through the arm and continue their orbit into the interarm region. The arm itself stays roughly in place, continuously refreshed by incoming gas from upstream. This is why the spiral arms are so visually prominent in photographs. They're marked by the youngest, most massive and most luminous stars. These stars are bright blue supergiants that can be 10,000 or 100,000 times more luminous than the Sun. They are so bright that they dominate the visual appearance of the arm, even though they're vastly outnumbered by older, dimmer stars. And they are also short-lived. Massive stars burn through their hydrogen fuel in just millions of years, compared to billions for stars like the Sun. So they don't survive long enough to drift far from where they formed. They form in the arm, blaze brilliantly for a few million years, and then explode as supernovae, often still within or near the arm region. The result is that the arms are continuously lit up by the birth and death of these massive stars. Between the arms, the older stellar population, stars that formed in the arms millions or billions of years ago, and have since drifted into the interarm regions, continues to orbit quietly. These are cooler, redder, dimmer stars, red dwarfs, orange K-type stars, yellow G-type stars like the Sun. They don't illuminate the gas around them in dramatic ways, and they far outnumber the bright massive stars, so the interarm regions look darker and emptier in photographs even though they contain a substantial stellar population. The distribution of stellar density across the galactic disk is real, but the visual impression exaggerates it, because our eyes are drawn to the brightest features. The Milky Way's spiral structure, as best we can determine from our embedded position, consists of 4 major arms: the Perseus arm, the Norma outer arm, the Scutum Centaurus arm, and the Sagittarius Carina arm, plus several shorter segments and spurs, including the Orion spur where our solar system lives. The Sun is not in a major arm, it's in a minor spur, which is why the night sky around us doesn't show dramatic concentrations of star-forming nebulae in any particular direction the way it might if we were embedded in a major arm. At the centre of the Milky Way, the situation is different again. Rather than continuing the disk pattern all the way to the centre, the Milky Way has a bar, an elongated rectangular structure of stars that cuts through the central bulge at an angle estimated to be about 25 to 30 degrees relative to our line of sight to the galactic centre. This bar is roughly 27,000 light-years long and is thought to contain between 30 and 40% of the entire stellar mass of the galaxy. It rotates as a rigid structure at a rate of about 35 to 40 kilometers per second per kiloparsec. Galactic bars are extremely common. About 2/3 of all spiral galaxies, including the Milky Way, have them. They form through gravitational instabilities in the inner disk of a galaxy, as stars are deflected from circular orbits into elongated ones that happen to be aligned with each other. When enough stars are aligned in elongated orbits, their combined gravity reinforces the elongated structure, creating the bar. The bar in turn affects the dynamics of everything around it, channeling gas inward toward the galactic center along the arms of the bar. This gas inflow feeds star formation in the central regions and can also feed the supermassive black hole at the very center, in the Milky Way, a 4 million solar mass black hole called Sagittarius A star. The bar also has effects on the outer disk, influencing the pattern speed and structure of the spiral arms. The combination of bar, bulge, disk, and spiral arms gives the Milky Way its particular spatial distribution of stellar density. Stars are most densely packed in the central bulge and bar. Density falls off going outward along the disk, with local enhancements in the spiral arms and local minima between them. The outermost disk is sparsest of all, and everywhere, at every radius, the density is far, far lower than you'd need to call it full, in any normal sense of the word. Section 7. Galaxy types and their different flavors of emptiness. Not every galaxy is a spiral galaxy, and the different types of galaxies express the same fundamental emptiness in different architectural styles. Understanding the variety of galactic morphology, the scientific term for shape and structure, is another way of understanding how gravity organizes matter into different patterns of concentration and void. Elliptical galaxies are the first major alternative to spiral galaxies, and they represent a dramatically different mode of galactic life. Elliptical galaxies have no flat disk and no spiral arms. Instead, they're three-dimensional, roughly egg-shaped or spherical distributions of stars. They come in a wide range of sizes, from relatively small ellipticals with tens of millions of stars to the giant ellipticals at the hearts of rich galaxy clusters that contain trillions of stars. The designation system for ellipticals runs from E0, which is nearly perfectly spherical, to E7, which is quite elongated. The stellar populations in elliptical galaxies are dramatically different from those in spirals. Spiral galaxies like the Milky Way have a mix of old and young stars. There's an ancient population of red and orange stars that formed billions of years ago, plus ongoing star formation producing young blue stars in the spiral arms. Elliptical galaxies, by contrast, are dominated overwhelmingly by old red stars. They have essentially stopped forming new stars. Their interstellar medium is depleted of the cold molecular gas that would fuel new star formation. What remains is a hot, diffuse gas pervaded by X-ray emitting plasma at temperatures of millions of Kelvin. Why did elliptical galaxies run out of gas while spirals are still forming stars? The leading explanation involves galaxy mergers. Most large elliptical galaxies are thought to have formed through the merger of two or more spiral galaxies. When two spirals merge, their gas-rich disks are disrupted and their gas clouds collide catastrophically, triggering an enormous burst of star formation, a starburst event that converts a large fraction of the available gas into stars very rapidly. Meanwhile, the merger also feeds gas to the central supermassive black hole, which becomes active as a quasar or active galactic nucleus, releasing enormous amounts of energy that heat the remaining gas and prevent it from cooling back down to form new stars. After the burst of activity subsides, the merged galaxy settles into an elliptical shape, with a depleted gas reservoir and little ability to form new stars. Elliptical galaxies also differ from spirals in their kinematics, the way their stars move. In a spiral galaxy, the stars in the disk are all orbiting in roughly the same direction, giving the galaxy its overall rotation. In an elliptical galaxy, the stars are moving in much more random directions, more like a swarm of bees than a rotating disk. Individual stars orbit the galactic center on various inclined and elongated paths, and the overall shape of the galaxy is maintained not by rotation, but by the balance of random stellar velocities. The largest galaxies in the observable universe are ellipticals, the so-called giant elliptical galaxies, or CD galaxies, found at the centers of rich galaxy clusters. the galaxy M87 in the Virgo cluster, which became internationally famous as the host of the first supermassive black hole ever directly imaged in 2019 by the Event Horizon Telescope, contains roughly 6 trillion stars, about 15 to 20 times more than the Milky Way. And yet, by the same arithmetic we worked through earlier, even M87's 6 trillion stars occupy a negligible fraction of its total volume. The Milky Way, currently a spiral galaxy, may eventually become an elliptical. The Andromeda Galaxy, our nearest large spiral neighbour, has long been predicted to collide and merge with the Milky Way, with the merged product being an elliptical galaxy nicknamed Milkomeda. However, as we'll discuss in the next section, recent research has significantly revised the probability and timeline of that collision. Irregular galaxies represent a third major category. Galaxies that fit neither the spiral nor elliptical classification, usually because they've been tidally distorted by interactions with neighbouring galaxies, or because they're simply too small and dynamically unrelaxed to have developed the orderly structure of larger galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches in the night sky, are classic examples of irregular galaxies. Both are satellite galaxies of the Milky Way, gravitationally bound to us and orbiting us at distances of about 160,000 and 200,000 light-years respectively. Both are currently undergoing elevated rates of star formation, partly triggered by the tidal interaction with the Milky Way. Dwarf galaxies, tiny galaxies containing anywhere from a few thousand to a billion stars, are the most numerous type of galaxy in the universe by count, though they contain only a small fraction of the total stellar mass. Our Milky Way alone has at least 50 known satellite dwarf galaxies, and the actual number, including ultrafaint dwarfs too dim to have been detected yet, is likely much larger. Some estimates suggest the Milky Way may have several hundred, or even over 1,000 satellite dwarfs once surveys are complete enough to detect the faintest ones. Each galaxy type, spiral, elliptical, irregular, dwarf, is mostly empty by our standard arithmetic. Each has organised its stars differently, through different histories of gas accretion and star formation and merger events. Each has a particular architecture of stellar density and void, but the fundamental physics of stellar size versus galactic volume means that none of them are anything other than overwhelmingly empty, however different their empty looks from each other. Section 8. When Galaxies Collide. The proof of emptiness in motion. Perhaps the most dramatic and visceral proof of how empty galaxies really are comes from observing and thinking carefully about what happens when two galaxies merge. The popular image is of a cataclysmic collision, stars smashing into each other, explosions everywhere, a kind of cosmic demolition derby. The reality is simultaneously more dramatic in some ways, and far less dramatic in the specific sense of stellar collisions. When two galaxies merge, the stars in each galaxy almost certainly do not collide with any stars in the other galaxy. The Wikipedia article on the Andromeda Milky Way collision states this directly. The chance of even two stars colliding is negligible because of the huge distances between the stars. When the Milky Way and Andromeda eventually merge, if they merge, as recent research suggests the probability is closer to 50-50 than the near certainty previously believed, the result will not be a firework display of stellar impacts. It will be more like two clouds of cigarette smoke mingling in an empty room. The individual particles pass through each other without touching. Only the bulk fluid behaviour matters. What actually happens in a galaxy merger is a story written entirely in gravity. As two galaxies approach each other, their dark matter halos, the extended invisible structures that surround each galaxy and are far larger than the visible stellar disk, begin to interact first. The halos overlap and interpenetrate, and their gravitational interaction begins to slow the galaxy's approach, and eventually cause them to turn around from what would otherwise be a flyby. Meanwhile, the stellar disks of the two galaxies begin to feel each other's tidal forces. The gravity of the approaching galaxy pulls differentially on different parts of the disk, stronger on the near side, weaker on the far side, stretching the disk and distorting it from its original circular shape into complex curved and elongated forms. These tidal distortions create the beautiful shapes that make interacting galaxies among the most photographed objects in the sky. The antenna galaxies in the constellation Corvus are a pair of colliding spiral galaxies that have developed dramatic curved tidal tails, streams of stars flung outward by the gravitational interaction, curving away from the main bodies of the galaxies in great arcs hundreds of thousands of light-years long. The mice galaxies, also called NGC 4676, show two long, thin tails of stars stretched out behind them like the tails of two mice. In each case, the tails are made of stars that have been pulled out of their original orbits by the tidal forces of the approaching companion galaxy. While all this dramatic gravitational sculpting is happening to the stars, the gas in both galaxies is having a completely different experience. Gas is a fluid. It can undergo shocks. When the interstellar media of two merging galaxies collide, the gas clouds ram into each other at relative velocities of hundreds of kilometers per second. These collisions produce strong shocks that compress the gas enormously, creating conditions far denser than any gas cloud would naturally achieve on its own. The compressed gas exceeds the gene's mass by a large margin and begins collapsing to form new stars at a furious rate, far faster than in a normal, quiescent galaxy. This is the starburst phase of a galaxy merger, and it can persist for hundreds of millions of years, converting enormous quantities of gas into stars until the reservoir is exhausted. The antenna galaxies, for instance, are currently in an early starburst phase, forming new stars at a rate roughly 10 times higher than the Milky Way's normal rate. There are thousands of new star clusters visible in the interaction region, ranging from compact young clusters just a few million years old to more evolved clusters tens of millions of years old. The gas that falls into the central regions of the merging galaxies can also trigger activity in the supermassive black holes, fueling them to become active galactic nuclei that pour out radiation and energetic jets, further disrupting the gas and inhibiting star formation in their vicinity. Eventually, after multiple passes, galaxies in a merger don't simply smash together once. The mutual gravitational attraction causes them to make multiple close passes, like two ice skaters caught in a death spiral, their orbits decaying with each pass. The two stellar systems lose enough orbital energy to fall together completely. The formerly separate disks are scrambled into a single, roughly spherical stellar distribution. The remaining gas has been consumed in star formation or driven out by feedback. The result is an elliptical galaxy, rounder, redder, and quieter than either of its spiral progenitors. Throughout this entire billion-year process, the probability of any two individual stars physically colliding remains vanishingly small. There's a slim possibility that in the very densest regions, the galactic nuclei where stellar density is highest, a few stars might undergo close enough encounters to collide or merge. But for the vast majority of stars in both galaxies, the merger is a gravitational experience, not a physical one. Their orbits are scrambled. They end up in new, complex orbits around the merged system's center of mass. But they themselves are untouched. The emptiness absorbs the violence. The updated research on the Milky Way-Andromeda merger, published in 2025 in Nature Astronomy by Till Sawala and colleagues at the University of Helsinki, is worth examining in some detail because it illustrates how even in dramatic celestial events, the uncertainty in our knowledge of the universe is itself revelatory. Previous estimates, based on Hubble Space Telescope measurements of Andromeda's transverse velocity, suggested that a head-on collision was nearly certain within 4 to 5 billion years. The new study incorporated updated measurements from both the Hubble and the Gaia mission and explicitly accounted for the gravitational effects of other members of the local group, particularly the Large Magellanic Cloud, a massive satellite of the Milky Way whose gravitational influence had previously been underestimated. With these corrections, the probability of merger within 10 billion years dropped to roughly 50%, and the probability of a direct head-on collision fell to less than 2%. Whether or not the Milky Way merges with Andromeda, the important point for our exploration is that even contemplating such a merger makes clear how empty these structures are. 2 trillion star galaxies approaching each other, destined to merge, and the stars simply pass through each other like ghosts. The emptiness is not just a fact about galaxies in isolation. It defines their behavior even in their most dramatic interactions. In Section 9, the cosmic web, emptiness, all the way up, we've been focused primarily on the emptiness within individual galaxies. But if you zoom out, way out past individual galaxies, past galaxy groups, past clusters, into the realm of the very largest structures in the universe, the pattern of emptiness continues and amplifies. The universe is organized at the largest scales into a structure called the cosmic web, and understanding the cosmic web is essential for understanding why galaxies are distributed the way they are, why some regions of the universe are crowded with galaxies and others contain almost none. The cosmic web is the large-scale structure of the observable universe, the arrangement of galaxies, galaxy clusters, and the matter between them across distances of hundreds of millions to billions of light-years. It gets its name from its appearance. In three-dimensional maps of galaxy positions, the universe looks somewhat like a spider's web or a cosmic foam, with densely concentrated filaments and sheets of galaxies surrounding vast, nearly empty spherical regions called voids. The filaments are the structural backbone of the cosmic web. They are long, thread-like concentrations of galaxies and dark matter that connect at dense knots called galaxy clusters and superclusters. A single galaxy filament can extend for hundreds of millions of light-years. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, is a filamentary structure about 1.4 billion light-years long, one of the largest coherent structures known in the observable universe. In 2025, astronomers announced the discovery of an even larger structure they named Quipu, which appears to extend across multiple billion light-years. Between the filaments lie the cosmic voids, and the voids are where the emptiness really becomes overwhelming. Individual cosmic voids range from roughly 30 million to 300 million light-years in diameter. The Bhuta's void, discovered in 1981, is roughly 330 million light-years in diameter, and was so startlingly empty when first found that some astronomers suspected an error in the data. It contains only about 60 known galaxies within its boundaries, where you'd expect many thousands based on the average galactic density. The Eridanus supervoid is even larger, perhaps 600 to 1,000 million light-years across, though its exact extent is debated. These voids occupy roughly 80% of the total volume of the observable universe. Most of the universe by volume contains essentially nothing: no galaxies, no significant concentrations of gas, no visible structures of any kind. The galaxies, clusters, and filaments that we see, as numerous and spectacular as they are concentrated in the remaining roughly 20% of the cosmic volume. The universe is much more like a Swiss cheese or a bubble foam than like a solid mass with occasional holes, mostly void, with matter concentrated in the thin walls and strings between the voids. The origin of this structure traces back to the very beginning. In the first fraction of a second after the Big Bang, the universe was a hot, dense, nearly uniform plasma. But nearly uniform is not exactly uniform. There were tiny quantum fluctuations in the density of matter, regions that were by a minuscule fraction of a percent denser or less dense than the surrounding space. These were not random. They were produced by a process called inflation, a period of exponential expansion in the very earliest moments that stretched quantum-scale fluctuations to macroscopic scales and imprinted them on the structure of the universe. Over the next hundreds of millions of years, gravity went to work on these tiny fluctuations. Regions that were slightly denser than average attracted more matter from their surroundings, becoming denser still. Regions that were slightly less dense lost matter to their surroundings, becoming emptier. The process was self-reinforcing. The denser a region got, the stronger its gravitational pull, the more matter it attracted, the denser it became. The less dense a region got, the weaker its gravitational influence, the more matter it lost, the emptier it became. Dark matter led the way in this process, as we discussed earlier. The hot plasma of ordinary matter in the early universe was subject to radiation pressure that resisted its gravitational collapse, creating a kind of cosmic acoustic wave pattern, pressure waves travelling through the hot plasma like sound waves, called baryon acoustic oscillations. These waves imprinted a characteristic scale on the distribution of matter, a preferred separation distance of about 500 million light-years that is still visible today in the distribution of galaxies. But dark matter, not coupled to the radiation pressure, was free to begin gravitating earlier, creating the initial overdensities into which ordinary matter would eventually fall. As the universe expanded and cooled, a moment came about 380,000 years after the Big Bang when the temperature dropped low enough for electrons and protons to combine into neutral hydrogen atoms, the epoch of recombination. At this moment, the universe became transparent to radiation for the first time, and the radiation that was released is what we detect today as the cosmic microwave background. After recombination, the ordinary matter was free to fall into the dark matter, overdensities already established. Gas fell into the gravitational wells along the dark matter filaments, cooled, and eventually formed the first stars and galaxies. The void regions, meanwhile, were being actively evacuated. As matter flowed gravitationally toward the overdense filaments and clusters, it drained out of the underdense void regions. The voids grew larger and emptier over time, their boundaries sharpening as matter concentrated on their surfaces and edges. Today's voids are the endpoints of this 13.8 billion year evacuation process. There's a fascinating additional component of the cosmic web that deserves mention, the warm-hot intergalactic medium, or WHIM. A significant fraction, perhaps 40 to 50% of all ordinary matter in the universe, is thought to exist not in galaxies or stars but in the filaments of the cosmic web, in the form of warm to hot gas at temperatures of 100,000 to 10 million Kelvin. This gas is so thin and hot that it emits mostly in soft X-rays and ultraviolet light, making it very difficult to detect directly. Astronomers have been hunting for the WHIM for decades, because early census estimates of ordinary matter found that a large fraction seemed to be missing from observable structures. The WHIM is where that matter is hiding, strung out in the cosmic web, not in galaxies, not in the voids, but in the filaments between them. The cosmic web represents the answer to why are galaxies where they are at the larger scales. They're where they are because of the initial density fluctuations amplified by gravity over cosmic time. The filaments are where the overdensities concentrated. The voids are where the underdensities emptied out. And the galaxies are the luminous markers of the densest regions, the tips of the cosmic icebergs, the visible fraction of a much larger dark matter structure that shaped everything. The Milky Way, with its 300 billion stars and its 100,000 light-year disk and its 600,000 light-year dark matter halo, is a single node in this cosmic web. It is part of the local group, which is part of the Virgo supercluster, which is part of the Laniakea supercluster, which is one filament in the cosmic web, surrounded on its void-facing sides by hundreds of millions of light-years of nearly empty space. We're in one of the relatively concentrated regions of the universe, and even here we are mostly empty. Section 10. What empty space actually isn't empty. Throughout this exploration, we've been careful to say that galaxies are mostly empty of stars rather than simply empty, because the spaces between stars and the spaces between galaxies are genuinely not empty in the physicist's sense. They're full of things, just not things that are easily seen or easily imagined. Let's take stock of everything that fills the apparent emptiness. The most obvious non-stellar contents of a galaxy are the gas and dust of the interstellar medium, which we've discussed at length. But beyond that thin gas, the interstellar medium is also filled with radiation, photons of every wavelength imaginable, travelling in all directions from every source of electromagnetic energy in the galaxy. Visible light from stars, ultraviolet light from hot, young, massive stars, powerful enough to ionize hydrogen gas for hundreds of light years. Infrared radiation from warm dust, re-radiated starlight that was absorbed and re-emitted at longer wavelengths. Radio waves from neutral hydrogen clouds, from supernova remnants, from pulsars, from active galactic nuclei. X-rays from gas being heated near neutron stars and black holes. Gamma rays from radioactive decay of freshly synthesized heavy elements in supernova remnants. And everywhere, in every cubic centimeter of the Milky Way and beyond, the cosmic microwave background. This is the relic radiation from the Big Bang, now cooled to a temperature of just 2.726 Kelvin by 13.8 billion years of cosmic expansion. It fills the universe uniformly, reaching every point in the galaxy from every direction. If your eyes could see microwave light, the entire sky, from any point in the galaxy, would glow with a nearly uniform, very faint warmth, the afterimage of the universe's birth. This background is so uniform and pervasive that it is inescapable. There is nowhere in the observable universe where it doesn't reach. Then there are cosmic rays. These are high-energy charged particles, mostly protons but also helium nuclei, heavier nuclei and electrons, travelling at close to the speed of light through the interstellar medium. They come from supernova explosions, from the relativistic jets and lobes of active galactic nuclei, and possibly from other energetic sources we haven't fully identified. The cosmic ray flux in the Milky Way is substantial, About 1 cosmic ray particle passes through every square centimetre of space every second. We receive them on Earth constantly. They're one of the background sources of radiation that our bodies are perpetually exposed to. Cosmic rays play important roles in the ISM. They ionize molecular cloud gas in regions where ultraviolet light can't penetrate, enabling chemistry and influencing the magnetic field coupling. They heat the gas in the ISM through collisions. They carry information about energetic events occurring throughout the galaxy. Neutrinos are another pervading component. The Sun alone produces about 65 billion neutrinos per square centimetre per second at Earth's surface. They pass through you right now in enormous numbers without interacting. But the Sun is just one of 300 billion stars in the galaxy, and many of those stars produce far more neutrinos during their deaths as supernovae than in their entire normal lives. A supernova releases roughly 10 to the power of 58 neutrinos in the few seconds of the core collapse. More energy in neutrinos in those few seconds than the Sun will emit in its entire 10 billion year lifetime. The galaxy is full of neutrinos from every supernova that has ever occurred, drifting through the ISM, essentially never interacting with anything, carrying the history of stellar death across billions of years. And dark matter. We've discussed the dark matter halo, but it's worth emphasizing that dark matter is not just surrounding the galaxy, it permeates the galaxy. The density of dark matter in the solar neighborhood, right here around the Sun, is estimated to be roughly 0.3 to 0.4 gigaelectronvolts per cubic centimeter in energy density units, or equivalently about 0.01 solar masses per cubic parsec. If dark matter particles have masses in the range that many theorists favor, a few times the proton mass, then there are something like 10 to 100 dark matter particles per cubic centimeter in the space around us right now. They're passing through your body, through the Earth, through everything at this moment, without any detectable effect. The empty space between the Sun and the nearest star is full of dark matter particles drifting silently through it. Then there's the quantum vacuum. Modern quantum field theory tells us that even in a region of space with no particles at all, a true vacuum, the vacuum itself has energy. The quantum fields that underlie all matter and force are never exactly at zero. They fluctuate at quantum scales, with virtual particles briefly appearing and disappearing. This vacuum energy is real and has measurable physical consequences. The Casimir effect, where two uncharged metal plates in a vacuum experience a slight attractive force due to quantum fluctuations between them, is the most famous demonstration. The vacuum energy of space may also be what cosmologists call the cosmological constant, the energy density of empty space itself, which is responsible for the accelerating expansion of the universe first discovered in 1998. Dark energy, which makes up about 68% of the total energy content of the universe, may simply be the energy density of the quantum vacuum. So the empty space between stars is filled with gas, dust, magnetic fields, cosmic rays, photons across the entire electromagnetic spectrum, the cosmic microwave background, neutrinos, dark matter particles, and the quantum vacuum energy that constitutes the substrate of space-time itself. Calling it empty is like calling a vast windswept high-altitude desert empty just because you can't see any houses. It's empty of some things. It is not empty of everything, and the things it contains are not incidental. They are essential to the ongoing story of the galaxy. The Section 11, the Fermi Paradox Connection, Emptiness and the Great Silence. Here is the question the emptiness of galaxies makes most haunting. If there are hundreds of billions of stars in the Milky Way, and if even a small fraction of them have planets, and if even a small fraction of those planets have conditions suitable for life, and if life arose on any of them and gave rise to intelligence and technology, then where is everybody? This is the Fermi paradox, named for the physicist Enrico Fermi, who first framed it in a casual lunchtime conversation at Los Alamos National Laboratory in 1950. Fermi noted that the numbers strongly suggest extraterrestrial civilization should exist, and that, given enough time, at least some should be capable of interstellar travel or at least interstellar communication. Given the age of the Milky Way, about 10 billion years, and the age of the universe, 13.8 billion years, there has been enormous time for civilizations to develop and potentially spread across the galaxy, and yet silence. No signals from other civilizations, no artifacts, no megastructures around distant stars, no radio leakage, nothing. In 1961, astrophysicist Frank Drake formalized Fermi's intuition into what became known as the Drake equation, a systematic framework for estimating the number of communicating civilizations in the galaxy at any given time. The equation multiplies together 7 factors: the rate of star formation in the galaxy, well constrained at about a few stars per year, the fraction of stars with planets, now known from exoplanet surveys to be high, most stars have planets, the number of habitable planets per star system, less certain but probably at least 0.1 to 1 on average, the fraction of habitable planets on which life arises, deeply uncertain, the fraction of life-bearing planets that develop intelligence, deeply uncertain, the fraction of intelligent species that develop detectable technology, deeply uncertain, and the average lifespan of such technological civilizations, most uncertain of all. Plug in optimistic values for the uncertain factors, and you get hundreds or thousands of civilizations in the Milky Way right now. Plug in pessimistic values, and you get much less than 1, meaning we might be genuinely alone in this galaxy. The Drake equation doesn't give an answer. It maps out our ignorance. What the emptiness of the galaxy does give us, though, is one important piece of context for the paradox. Even if there are many civilizations out there, the vast distances between star systems make communication and contact extraordinarily difficult. A radio signal traveling at the speed of light takes 4 years to reach Proxima Centauri. It takes 100,000 years to cross the Milky Way. Even if some alien civilization beamed a powerful radio signal directly at us, we'd need to be listening in the right direction, at the right frequency at the right time, and the signal, spreading outward in all directions at the speed of light, loses power as the square of the distance. A signal 100 light-years away is 10,000 times weaker than the same signal at 1 light-year. The emptiness means that even a galaxy teeming with life might remain silent from any one civilization's perspective simply because the distances prevent contact on any meaningful timescale. We've had radio technology for about 120 years. Our broadcasts have reached a sphere of space only 120 light-years in radius, a tiny bubble in the galaxy. If there's a civilization 1,000 light-years away, they've been receiving our broadcast for 0 years, and they'd have to happen to be listening in our direction at the right frequency at the right time to pick up anything from us. Recent research has also raised the possibility that the Fermi paradox might have a simpler explanation than we've sometimes assumed. Intelligent life capable of interstellar communication might simply be very rare. A 2024 paper in Scientific Reports added 2 new factors to the Drake equation: the fraction of habitable planets with both continents and oceans, and the fraction with long-lasting plate tectonics, and found that these geological requirements dramatically reduce the expected number of communicating civilizations. The lead author concluded that both our planet Earth with continents, oceans, plate tectonics, and life, and our active, communicative, technological human civilization are extremely rare and unique in the entire galaxy. If that's right, if Earth-like planets with Earth-like geology are genuinely rare, then the emptiness of the galaxy and the silence of the Fermi paradox might both be telling us the same thing, that the particular kind of planet and planetary system that gave rise to us is something the universe doesn't do very often. We're not just in an empty galaxy. We might be in an empty galaxy in the most important possible sense, empty of minds. Or not. We genuinely don't know. And the not knowing is perhaps the most honest place to be. Section 12. Closing. What the emptiness means for us. So we've come a long way from the original question. Why are most galaxies empty when they have billions of stars? The short answer is, because the universe is very, very big. Scale defeats density so completely that even billions of stars are negligible compared to the volumes that contain them. Stars occupy roughly 10 to the power of -21 of a typical galaxy's volume, a number so small it has no name in everyday language. The longer, richer answer involves everything we've explored tonight. The emptiness isn't random or accidental. It's the specific, physics-determined consequence of how gravity operates on matter across cosmic timescales. It reflects the low efficiency of star formation, driven by the balance between gravitational collapse and thermal pressure, and disrupted by the feedback from the stars themselves. It reflects the distribution of gas in molecular clouds, rather than uniformly throughout the disk. It reflects the shaping influence of dark matter halos, which determined the size and rotation of galaxies. It reflects the density wave structure of spiral arms, which concentrates star formation in some regions and leaves others relatively quiescent. And at the larger scales, it reflects the cosmic web, the filaments and voids that represent the amplified echoes of quantum fluctuations from the first moments of the Big Bang. The emptiness is also not emptiness in any absolute sense. The spaces between stars are filled with gas, dust, magnetic fields, cosmic rays, neutrinos, photons of all wavelengths, dark matter, and the quantum vacuum energy of spacetime itself. What we call empty is merely empty of stars. The rest of physics is still present, still operating, still doing important things. The interstellar medium is the repository from which future stars will form, the medium through which stellar feedback travels, and the slow-motion chemistry lab where organic molecules are assembled over millions of years. The darkness between the stars is not dead. And what does the emptiness mean for us, as beings who live on a rocky planet around an ordinary star in the quiet suburbs of a galaxy, in a filament of the cosmic web? It means we are extraordinarily improbable. The particular sequence of events that led to a planet with the right size and distance from its star and plate tectonics, and oceans and continents, and the right chemistry, in the right configuration to generate self-replicating molecules, and then multicellular life, and then nervous systems, and then the kind of nervous system capable of asking questions about galaxies. That sequence was never guaranteed. The universe could have been full of stars for its entire history with not a single mind to contemplate them, and by all the evidence we have, it very nearly is. It means we are isolated. The distances between stars are so vast that even our fastest imagined spacecraft would take tens of thousands of years to reach the nearest one. The nearest galaxy is 2.5 million light-years away. The observable universe extends 46 billion light-years in every direction. We are, for any practical purpose, alone on our island, in an ocean so vast that it effectively cannot be crossed. The stars we see are all we will ever have direct access to. The emptiness is the fence of our world. But here is what I find genuinely beautiful about all this. The thing I keep coming back to when I think about cosmic emptiness. The emptiness is why we're here. The particular kind of planetary system that gave rise to Earth, with its long-lived stable star and its quiet neighborhood, and its 4.5 billion years of geological and biological evolution, required exactly the kind of spacious, low-density environment that characterizes our galactic neighborhood. If stars were 10 times closer together, the radiation and gravitational environment would be chaotic, disrupting planetary orbits, bombarding planets with energetic particles, preventing the slow, stable chemistry of life from getting started. The emptiness, the specific physics-determined emptiness of our corner of the galaxy, may be a prerequisite for our existence. The universe is mostly nothing, mostly void, mostly darkness, mostly silence. The stars are rare, planets are rarer still. Complex life, if it exists anywhere else at all, is rarer than that, and minds capable of looking up at the vast emptiness and wondering about it. We might be the rarest thing of all. You're made of matter, forged in the hearts of ancient stars, organized by billions of years of chemistry and biology into a being capable of contemplating the cosmos. The atoms in your body were synthesized in stellar interiors and scattered into the interstellar medium by supernova explosions, and drifted through the galactic void for billions of years before being incorporated into the solar nebula that formed the Sun and Earth. You are, in a very literal sense, made from the emptiness, made from the thin wisps of stardust that drifted between the stars, waiting to find a home. The galaxy is mostly empty, but not at the coordinates where you're standing. Here, somehow, impossibly, there is something rather than nothing, and that something is looking up. If tonight's exploration of cosmic scale and the profound nature of emptiness left you with questions, or if it changed the way you look at the night sky, I want to hear about it. Drop your thoughts in the comments. Tell me what surprised you most, what you're still puzzling over, what you want to explore next. The best part of this community is the conversation, and there are no small questions when we're talking about the universe. If you found value in tonight's journey, the best thing you can do is like this video and subscribe to the Cosmic Pup. We keep digging into the deep questions, the ones that have no easy answers but are worth asking anyway. And we're going to keep going for a long time. Every subscription, every share helps us reach people who are looking for exactly this kind of exploration. The universe is vast, it is mostly dark, it is mostly empty, and it is extraordinary. We'll see you next time. Script for the Cosmic Pup topic. Why are most galaxies empty when they have billions of stars? Research conducted May 2026. All astronomical facts drawn from peer-reviewed. Literature, NASA, ESA, the National Radio Astronomy Observatory, an established cosmological consensus. Where science is actively debated, this has been noted. Speculative statements are labelled as such. Supplementary section. The life and death of stars. How emptiness is created and enriched. There's a dimension of galactic emptiness we haven't fully explored yet, and it's one of the most poetically important. The role that stars themselves play in shaping the emptiness around them. Stars are not passive points of light suspended in a static void. They are engines of transformation, constantly churning matter and energy through the interstellar medium, sweeping out enormous bubbles of hot plasma, seeding the galaxy with the heavy elements that make chemistry and biology possible, and dying in explosions so powerful they can trigger new waves of star formation hundreds of light years away. The emptiness of the galaxy is partly a product of the stars themselves. Let's trace what a star actually does to its neighbourhood over its lifetime, using our Sun as the template, and then imagine scaling this up to the billions of stars doing the same thing across the galaxy over billions of years. The Sun was born about 4.6 billion years ago in a molecular cloud, not unlike the dense cold gas clouds we've discussed. At the moment of its birth, the surrounding gas was dispersed by the early solar wind, the outflow of charged particles from the young Sun's surface, and by the radiation pressure of the Sun's growing luminosity. This swept the raw material of the birth cloud away, creating a clean zone around the infant solar system. Those building materials that weren't swept away were assembled, through processes of accretion and gravitational clustering, into the planets, moons, asteroids and comets that orbit the Sun today. For the next 4.6 billion years, and for another 5 billion years to come, the Sun pumps out energy at a rate of about 3.8 times 10 to the power of 26 watts. Every second, the Sun converts about 4 million metric tons of its mass into pure energy through nuclear fusion. Over its entire 10 billion year main sequence lifetime, the Sun will fuse perhaps 5% of its mass, about 0.05 solar masses, or about 50 times the mass of Jupiter, into helium and heavier elements, with the mass difference radiated away as light and heat. The Sun also continuously blows a solar wind, a stream of charged particles, mostly protons and electrons, streaming outward from the Sun's corona at speeds of 400 to 800 kilometers per second. This solar wind carves out a region of space called the heliosphere, a vast bubble extending to about 100 to 120 times the Earth-Sun distance, called astronomical units, or AU. Within the heliosphere, the solar wind dominates the particle environment. Beyond the heliopause, the boundary of the heliosphere, the interstellar medium takes over. The Voyager 1 spacecraft crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. This is the sphere of influence of just one star. 120 astronomical units, about 18 billion kilometers, is the territory that one medium-sized star sweeps clear of the interstellar medium. In light years, that's only about 0.0019 light years. Tiny compared to the 5 light-year average spacing between stars. Our Sun barely makes a dent in the surrounding void. But now consider what happens when a star is much more massive. A star 10 times the mass of the Sun is roughly 10,000 times more luminous. Its radiation pressure on the surrounding gas is 10,000 times stronger. Its stellar wind blows 10 to 100 times more mass per year than the Sun's wind, and at higher velocities. The ultraviolet radiation from such a massive star, an O-type or early B-type star, is powerful enough to ionize hydrogen gas in a sphere hundreds of light years in radius. These are the H2 regions we discussed earlier, glowing bubbles of ionized gas surrounding massive young stars. The Orion Nebula, for instance, is powered primarily by a small cluster of massive young stars called the trapezium, and it extends about 24 light-years in diameter. As these massive stars age through their brief lives, only a few million years for the most massive, they continue to sweep material out of their vicinity. The combination of radiation pressure, stellar wind, and the expanding HYI region creates a bubble of low-density hot gas around the star and its siblings. Dense molecular cloud material that forms the walls of the bubble is compressed and can trigger new waves of star formation around the edge, a process called triggered star formation, where one generation of stars initiates the formation of the next. And then the massive star dies. In a core collapse supernova, the star's iron core implodes in a fraction of a second, releasing a gravitational energy of roughly 3 × 10⁻46 joules, more energy than the Sun will emit over its entire lifetime, and most of it released in the form of neutrinos in just seconds. The blast wave from the explosion races outward through the ISM at thousands of kilometers per second, sweeping up gas and dust into a thin, dense shell and heating the gas inside the shell to temperatures of millions of Kelvin. The result is a supernova remnant, an expanding bubble of hot plasma and compressed gas that can grow to hundreds of light-years in diameter before finally dissolving into the ISM. Supernova remnants are one of the primary sources of the hot ionized medium we discussed earlier. They're also one of the primary sources of cosmic rays. The energetic charged particles that permeate the ISM are accelerated at supernova shock fronts to relativistic velocities through a process called diffusive shock acceleration. And they are the primary source of the heavy elements heavier than iron. When the shock wave from a supernova passes through the envelope of the exploding star, it triggers explosive nucleosynthesis, creating elements from iron up through uranium and beyond through a cascade of rapid neutron captures. All of the gold, platinum and uranium in your body and in Earth's crust was created in events like these, or in even more energetic events like the merger of 2 neutron stars, which are the collapsed remnants of stellar explosions. This means that every supernova effectively creates a new region of emptiness in the galaxy, a bubble of hot, diffuse gas carved out of what was previously a denser ISM. In a galaxy that has experienced billions of supernovae over its lifetime, these bubbles are everywhere. They overlap, merge, create complex networks of cavities and compressed shells. The local bubble that the Sun currently inhabits, a region of unusually hot, thin ISM, extending perhaps 300 light-years in diameter around us, was carved out by a series of supernovae that occurred roughly 10 to 20 million years ago, when a cluster of massive stars formed nearby and then exploded in quick succession. We live in a supernova bubble, shaped by stellar deaths that happened long before the solar system was even formed in its current configuration. This supernova bubble structure is another layer of texture to galactic emptiness. The galaxy is not uniformly empty on the scale of individual stellar neighborhoods. It's a complex foam of bubbles, regions swept clean by stellar radiation and explosions, nestled against compressed shells of swept-up gas, which in turn border new molecular clouds triggered by the compression. The empty regions are not the result of nothing having happened there. They are the result of something having happened there. A star was born, it lived, it died, it blew its neighborhood clean. Now scale this up. The Milky Way has experienced somewhere between 100 million and 1 billion supernova explosions since it formed. Every one of those supernovae created a bubble, compressed a shell, potentially triggered new star formation, and seeded the surrounding ISM with heavy elements. The complex, multi-phase, turbulent, magnetically structured interstellar medium we described earlier is the cumulative product of all those explosions, layered on top of each other over billions of years. The galaxy's ISM remembers its history. Every filament, every void, every dense molecular cloud carries the imprint of ancient stellar deaths. This also means that the chemical composition of the galaxy has been continuously evolving. The first stars formed from pure hydrogen and helium, the only elements that existed after the Big Bang, with trace amounts of lithium. Those first massive stars fused hydrogen into helium into carbon and oxygen, and exploded as supernovae, seeding the surrounding gas with these heavier elements. The next generation of stars formed from gas enriched in carbon and oxygen. They fused heavier elements in turn, and when they exploded, they added still heavier elements to the mix. Over 10 billion years of this cycle, the ISM has been progressively enriched in what astronomers call metals, all elements heavier than helium, to the point where today's molecular clouds contain all the elements necessary for rocky planets and organic chemistry. The Sun formed from a gas cloud already enriched by multiple previous generations of stellar evolution. The oxygen in our atmosphere, the carbon in our DNA, the calcium in our bones, the iron in our blood, all of it was synthesized in stars that lived and died before the sun formed. We are, in the most literal possible sense, recycled star matter. The emptiness between the stars is the medium through which that matter was transported between stellar generations. The void is not empty of our history. It carried us here. Supplementary section, the galactic center, where emptiness ends. Throughout this discussion, we've mostly been talking about the kind of emptiness that characterizes the disk of the Milky Way, the suburbs of the galaxy where our solar system lives. But the galaxy has a center, and the galactic center is as different from our neighborhood as a city center is from rural countryside. Understanding the galactic center, and why it is so different from the surrounding disk, adds another dimension to our appreciation of galactic structure and emptiness. At the very center of the Milky Way, some 26,000 light-years from Earth, lies one of the most extreme environments in the galaxy. The stellar density in the central parsec, a region roughly 3.26 light-years across, is extraordinary. In the solar neighborhood, stars are separated by an average of about 5 light-years. In the galactic center, stellar separations can be measured in light weeks to light months. The night sky viewed from a planet in the galactic center would be almost incomprehensibly brilliant. There would be no true night. Stars would cover the sky in numbers that would make our star-studded sky look barren by comparison. And at the very center of this dense stellar environment sits a supermassive black hole, Sagittarius A star, weighing in at about 4 million solar masses. Black holes cannot be seen directly. Their gravity is so extreme that not even light can escape from within the event horizon, but their gravitational influence on surrounding matter is unmistakable. Astronomers have spent decades tracking the orbits of stars very close to the galactic center using infrared telescopes, and the precision of those orbital measurements, particularly of a star called S2, which orbits Sagittarius A star in just 16 years, completing an ellipse that takes it within about 120 astronomical units of the black hole at closest approach, has allowed them to measure the mass of the central black hole with extraordinary precision. The Keplerian orbital dynamics of S2 and other stars near Sagittarius A star are a direct measurement of general relativistic gravity in an extreme environment. Sagittarius A star is currently a relatively quiet black hole. It accretes mass at a low rate and doesn't have the powerful jets and enormous luminosity of the quasars in distant young galaxies. But there is strong evidence that it was much more active in the past. The Fermi bubbles, two enormous lobes of hot gas extending about 25,000 light-years above and below the galactic plane, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, are thought to be the remnants of a period of enhanced activity from Sagittarius A star a few million years ago, when it was accreting gas at a much higher rate and driving powerful outflows that inflated the bubbles. The galactic center region is also home to some of the most massive and luminous stars in the galaxy. Young stars recently formed from dense gas clouds. Paradoxically, despite the harsh conditions near the black hole, intense radiation, powerful tidal forces, star formation is occurring in this region. The Arches cluster and the quintuplet cluster, both within 100 light-years of the galactic center, are young massive star clusters, probably no more than a few million years old, containing some of the most massive stars known. The Pistol star, in the quintuplet cluster, is estimated to be between 80 and 150 times the mass of the Sun, and is one of the most luminous stars in the galaxy, emitting roughly 10 million times more power than the Sun. The galactic center also contains a complex of molecular clouds, with conditions unlike anything in the disk. The central molecular zone, a region within about 500 light-years of the galactic center, is far denser and warmer than typical molecular clouds, with gas temperatures of a few hundred Kelvin rather than the 10 to 30 Kelvin characteristic of disk molecular clouds. The gas in the central molecular zone is highly turbulent and pervaded by strong magnetic fields, making star formation there operate quite differently from the disk. All of this, the dense stellar population, the supermassive black hole, the massive young star clusters, the complex molecular gas, contrasts sharply with the emptiness of the disk. The galactic center is not empty. By our disk standards, it's almost impossibly full. But even there, the absolute arithmetic of stellar volume versus available volume still plays out in the same direction. Even the densest stellar environments in the galaxy are still overwhelmingly empty by any non-astronomical standard. The difference between the galactic centre and our neighbourhood is the difference between 1 star per few light weeks versus 1 star per 5 light years, both orders of magnitude emptier than anything we can directly experience. Supplementary section: Exoplanets, Habitable Zones, and the Rarity of Inhabited Emptiness. We've talked a lot about the emptiness of the galaxy in terms of stars, but for life, what matters isn't just stars, it's what surrounds them. And here the emptiness becomes even more profound, because even among the hundreds of billions of stars in the Milky Way, the fraction that might host the specific conditions for complex life appears to be quite small. Since the mid-1990s, astronomers have discovered thousands of planets orbiting other stars, exoplanets. The Kepler Space Telescope, launched in 2009 and operated until 2018, alone detected over 2,600 confirmed exoplanets and many thousands of additional candidates by watching for the slight dimming of starlight when a planet passes in front of its star. Combining the Kepler results with those of other surveys, astronomers now estimate that on average, every star in the Milky Way has at least one planet. Many stars have multiple planets. If you take 300 billion stars and multiply by an average of at least one planet per star, you get at least 300 billion planets in the Milky Way, possibly a trillion or more. Of those planets, what fraction might be suitable for life? The usual starting point is the habitable zone, the range of distances from a star at which liquid water could exist on a planet's surface, given that the planet has an Earth-like atmosphere. This is sometimes called the Goldilocks zone, not too hot, not too cold. For a Sun-like star, the habitable zone extends roughly from about 0.95 to 1.4 times the Earth-Sun distance. For dimmer red dwarf stars, which make up about 70% of all stars in the galaxy, the habitable zone is much closer in. NASA estimates that there are perhaps 11 billion Earth-sized planets in the habitable zones of Sun-like stars in the Milky Way. When you include red dwarf stars, the number may be much higher, perhaps 40 billion or more. Of the planets we know about 20 to 30% of Sun-like stars appear to have an Earth-sized planet in or near the habitable zone. But habitable zone location is just the beginning. A planet can be in the habitable zone and still be completely unsuitable for life as we know it. Venus is technically within the outer edge of the Sun's habitable zone, or very close to it, but its surface is 465 degrees Celsius with a crushing atmosphere of carbon dioxide and sulfuric acid clouds. Mars is within the habitable zone as well, but it lost its magnetic field early in its history, which allowed the solar wind to strip away most of its atmosphere, and today its surface is far too cold and dry for liquid water under current conditions. For a planet to maintain liquid water and the conditions for complex chemistry over billions of years, it needs more than just the right distance from its star. It needs the right size, large enough to maintain a substantial atmosphere and geological activity, but not so large that it becomes a gas giant. It needs plate tectonics, which cycle carbon dioxide in and out of the atmosphere and regulate the long-term climate. It probably needs a large moon, which stabilizes the planet's axial tilt and prevents wild climate swings. It needs a magnetic field to protect it from stellar particle radiation. It needs its star to be old enough and stable enough that the planet has had time to develop complex chemistry. Recent research has suggested that Earth-like geology, specifically the combination of continents, oceans, and long-lived plate tectonics, may be considerably rarer than previously assumed. Plate tectonics requires the right balance of volatile elements in the crust, the right size of planet, the right thermal evolution. Many planets that are Earth-sized and in the habitable zone may lack plate tectonics, and therefore lack the climate regulation mechanism that has kept Earth habitable for 4 billion years. When you start multiplying all of these probability factors together, the number of truly Earth-like planets with the right size, distance, geology, chemistry, and stellar environment for complex life to potentially develop over billions of years, shrinks dramatically from the initial 11 to 40 billion estimate. Nobody knows what the right numbers are for the uncertain factors, but it's entirely possible that truly Earth-analogous planets are rare, perhaps even rare enough that Earth itself is one of a very small number in the galaxy. And then, even on the right kind of planet, life has to actually start. Abiogenesis, The transition from chemistry to biology, from complex organic molecules to self-replicating systems capable of Darwinian evolution, remains one of the deepest unsolved problems in science. We know it happened here, on Earth, sometime in the first billion years of the planet's existence. We don't know how hard it was, whether it was a nearly inevitable consequence of Earth's chemistry, or an enormously unlikely accident that required specific conditions to obtain. If abiogenesis is common, then many habitable planets harbour life. If it's rare, then even the right kind of planet might sit empty and lifeless for its entire existence. And beyond the origin of life, there's the question of complexity. Life on Earth existed for about 3 billion years as single-celled organisms, bacteria and archaea. Before the first multicellular life appeared, complex animal life with nervous systems and behaviour and eventual intelligence required billions more years. There's no guarantee that life on another world would follow the same path, or that intelligence and technology would ever emerge. The path from the first self-replicating molecule to a species capable of building radio telescopes and launching spacecraft is very long and required an enormous number of specific developments, each of which could have failed to occur. All of this is to say, the galaxy has room for life. It has hundreds of billions of stars. It has probably trillions of planets. It has 10 billion years of history in which chemistry could be operating on those planets. But the fraction of that enormous parameter space that actually produces complex, intelligent, communicating life might be extraordinarily small. The physical emptiness of the galaxy, the vast distances between stars, might be paralleled by a biological emptiness. Most of the stars shine on planets that are cold or airless, or too hot or simply lifeless, not because life is impossible in principle, but because the specific conditions required are rare enough that most planets never achieve them. The emptiness of the galaxy, considered in full, is therefore emptiness on multiple levels: empty of stars relative to its volume, empty of habitable planets relative to its stars, and potentially empty of living worlds relative to its habitable planets. Each level of emptiness amplifies the rarity of anything that does achieve the specific conditions required. We live in a galaxy of vast emptiness in every sense, and the fact that at least one point in this galaxy the emptiness gave way to chemistry, and then to biology, and then to consciousness is, if you really sit with it, something that should fill you with a sense of genuine wonder every single time you look up at the sky. Supplementary section: The Fate of the Galaxy. Emptiness in Deep Time. We've been discussing the galaxy as it is now, 13.8 billion years after the Big Bang. But the galaxy has a future as well as a past, and thinking about that future adds one final perspective on galactic emptiness that I find genuinely moving. The Milky Way is currently forming new stars at a rate of roughly 1 to 3 solar masses per year. This rate has been declining from a peak that occurred several billion years ago, when the galaxy was younger and had more cold gas available. The current star formation rate is sustainable for a few billion years before the gas reservoir begins to run seriously low. Meanwhile, the stars that already exist are aging. The Sun has about 5 billion more years of main sequence life before it exhausts its hydrogen fuel and expands into a red giant. Low-mass red dwarf stars, which make up the majority of all stars in the galaxy and are far more fuel-efficient than the Sun, will burn for tens to hundreds of billions of years. The very smallest red dwarfs may burn for 1 trillion years or more, 70 times the current age of the universe. On timescales of tens of trillions of years, the Milky Way, merged or not merged with Andromeda, will run out of gas. Star formation will cease entirely. The galaxy will enter a long, slow phase sometimes called the degenerate era. A population of slowly cooling white dwarfs, the remnants of sun-like stars, alongside neutron stars and black holes from the remains of massive stars, and the vast majority of the stellar population as extremely long-lived but very dim red dwarfs. The galaxy will still exist as a gravitationally bound structure, but it will be dark, most of its stars too faint to be seen from any distance, barely glowing in the infrared, cooling slowly toward absolute zero. Eventually, on timescales of 10 to the 14th to 10 to the 15th years, quadrillions of years, even the last red dwarfs will exhaust their fuel. The galaxy will contain only stellar remnants, white dwarfs cooling toward absolute zero, neutron stars gradually losing their spin energy, and black holes. And then, on truly extraordinary timescales, perhaps 10 to the 40 years or more, if proton decay occurs as some theories predict, even the white dwarfs will evaporate. The last macroscopic matter in the galaxy will be black holes, and eventually, on timescales of perhaps 10 to the 67 to 10 to the 100 years, even the black holes will evaporate through Hawking radiation, converting their mass slowly and completely into radiation. At the end of this process, the galaxy will be empty in a deeper sense than it has ever been in its history. Not just mostly empty, but truly, perfectly empty of any structured matter at all. Just a diffuse haze of radiation expanding forever into the cold dark of an accelerating universe, the last faint echo of all the stars that ever were. We are, cosmically speaking, in the early morning of the universe. The stars are still forming, the galaxy is still active. Life, if it exists anywhere, is young in cosmic terms, with trillion-year timescales of potential stellar neighbours ahead of it. The emptiness of the current galaxy, profound as it is the emptiness of a galaxy at peak activity. Still building, still burning, still cycling matter through stars and back to the ISM in an ongoing loop. The deeper emptiness is coming eventually over timescales so vast that the entire history of the observable universe so far is but a brief flash. We happen to live in the bright, early moments when the universe still burns with purpose. That might be the most important thing the emptiness tells us about our place in time. We are not late to the party, we are, in cosmic terms, extraordinarily early. The universe has barely begun. Supplementary section, The Anthropic Perspective, Why We Live Where We Do in the Emptiness. There's a question that might seem philosophical, but turns out to have genuine scientific content. Why do we find ourselves in this particular region of the Milky Way? Not in the galactic centre, not on the outer edge, not in a dense star-forming cloud, not in an empty interarm void, but here, in the Orion Spur, orbiting a relatively ordinary yellow dwarf star at a comfortable distance from the galactic centre. Part of the answer is simply statistics. Most stars in the galaxy are somewhere in the disk, at intermediate galactic radii, and so simply by the statistics of stellar distribution, most inhabited planets in the galaxy, if there are any, would be somewhere in the disk. But there are additional physical reasons why the galactic suburbs might be particularly well suited to harbouring complex life, and they connect directly to the nature of galactic emptiness we've been exploring. The galactic centre, despite its density of stars, is a harsh environment in ways that might make complex life difficult. The radiation environment near the galactic centre is extreme. The supermassive black hole periodically flares with energetic emissions. Supernovae are more frequent in the dense central regions than in the disk, because star formation is more active there. The higher density of stars means that any planetary system is more likely to be gravitationally perturbed by passing stars over geological timescales. Passing stars can scatter comets and asteroids onto planet-crossing orbits, triggering bombardment events that could disrupt developing biospheres. The stronger tidal forces in the galactic centre can destabilize planetary systems that would be perfectly stable in our quieter neighbourhood. The galactic outer edge, meanwhile, has the problem of being very old and very metal-poor. The outer disk received the least enrichment from the supernova-driven recycling of stellar material that built up the heavy element content of the galaxy over billions of years. Stars in the outer disk tend to have lower abundances of elements like carbon, oxygen, iron, and silicon, the elements that are necessary for rocky planet formation and for the biochemistry of life as we know it. Without enough iron and silicon and other heavy elements in the protoplanetary disk, a forming planet can't build up a substantial rocky bulk. Without enough carbon and oxygen and nitrogen, the organic chemistry of life can't get started. Our location at about 26,000 light-years from the galactic centre, roughly in the middle of the disk in terms of radius, happens to be in what some researchers have called the galactic habitable zone, a ring of galactic space that is enriched enough in heavy elements for rocky planet formation, but not so close to the galactic centre that the radiation and dynamical environment becomes prohibitively hostile. This galactic habitable zone concept is contested. Not all researchers agree on its precise boundaries, or even whether it's a meaningful concept, but the general idea that our specific location in the galaxy isn't arbitrary resonates with the physical realities we've been discussing. There's also the matter of our spiral arm location. We're in the Orion Spur, a minor arm segment, not a major spiral arm. Major spiral arms are regions of active star formation, dense gas clouds, intense radiation from newly formed massive stars, and frequent supernova explosions. Being embedded in a major arm could mean higher doses of radiation, more frequent disruptions from stellar feedback, and a more chaotic dynamical environment. Our position in a quieter interarm spur might give the Earth-Sun system a more stable, sheltered environment, the cosmic suburbs rather than the urban core. This is a version of what philosophers call the anthropic principle. We observe what we observe because we are here to observe it. If complex life requires particular conditions, then by definition any life form that develops to ask, "Why are we here?" must find itself in a place where those conditions are met. We're not in the galactic center because the galactic center is inhospitable. We're not in the outer galactic desert because it lacks the heavy elements for rocky planets. We're in the galactic suburbs because that's where the galactic suburbs are, and the galactic suburbs happen to be a relatively good place for complex chemistry to develop over billions of years. The emptiness of the galaxy on this view is not just a physical fact to be described, it's part of the selection effect that places us where we are. We live in a low-density environment because low-density environments, with their stable conditions and lower background radiation and quieter dynamical histories, may be more conducive to the development of complex life. The emptiness is, in this sense, part of the enabling condition for our existence. Zoom out one more step. We live not only in a relatively quiet part of the Milky Way, but in a galaxy that is a member of a relatively average-sized galaxy group, the local group, in a relatively average density region of a supercluster, Laniakea, that is nowhere near any of the most extreme environments in the cosmic web. We're not in a rich galaxy cluster with thousands of galaxies, where the intergalactic medium is hot and dense and active galactic nuclei are pumping radiation throughout the cluster volume. We're in a more modest neighborhood, and that modesty might itself be part of why this is a good place to be a life-bearing planet. The universe's emptiness, operating at every scale from the space between stars to the cosmic voids between galaxy filaments, may be inseparable from its hospitality to life. A universe without emptiness, filled to capacity with matter and energy, would be so hot and chaotic that chemistry couldn't operate. A universe with more emptiness, one in which even the slight density fluctuations of the Big Bang didn't grow into galaxies and stars, would have no nuclear reactors to forge the heavy elements, no supernovae to scatter those elements through the ISM, no rocky planets to collect those elements, and no chemistry to organize them into biology. The specific amount of emptiness in our universe at every scale is part of what makes it a universe where we can exist to notice the emptiness. The void between the stars is not the opposite of life. It is part of the conditions that permit life, in at least one small corner of a mostly empty galaxy, to emerge and ask why everything else is so empty. That circularity, the emptiness enables the observer who notices the emptiness, is, I think, one of the most beautiful ideas in cosmology. It doesn't resolve the questions. It doesn't tell us whether we're alone in the galaxy or accompanied by millions of other minds asking the same questions. But it does suggest that the emptiness itself is not accidental, not meaningless, not just the absence of something better. The emptiness is part of the structure of a universe that can, in principle, be understood. And that is extraordinary. The night sky is waiting for you. Every point of light up there is a sun. Most of them have planets. A vanishingly small fraction of those planets might be asking these same questions tonight, and all of them, every star, every planet, every wandering mind, are floating in an emptiness so profound that describing it accurately requires numbers that have no everyday meaning. Go outside tonight if you can, find a dark patch of sky, look up, let yourself feel the scale of what you're looking at, not just the stars but the space between them, the void that is almost everything, and know that you are a rare, improbable, extraordinary concentration of matter and energy that has organized itself against all apparent odds into something capable of wondering about its own existence. The universe is mostly empty, but here, right here it isn't. So, bye-bye and sleep well.